Hello, this is Mr. Howard. In this video we are going to look at polynomial applications and specifically using polynomials to maximize the volume of an object. And in the first example we will look at making a box without a lid from a given size of material and maximizing that volume. And then in the second example we'll look at doing the same thing, only the box will have a lid. And yes, this is actually done in the real world when companies are looking at packaging items and anything where a volume is concerned and they are trying to be as efficient as possible with material. Obviously, if you're a large corporation, you don't want to spend a lot of extra money on your packaging by having a lot of waste involved. So maximizing the volume from a given size sheet of raw material only makes sense, and it is a cost savings measure. Alright, so let's look at example 1 here. It says a box without a lid. Alright, a box without a lid is to be made from a rectangular sheet of cardboard 8 inches by 10 inches by cutting out the small square from each of the four corners and then folding up the sides to form a three-dimensional rectangular box. Make a diagram of the flat sheet with the squares cut out of each corner. Okay, we'll need to do that. Make a diagram of the 3D box. Okay, we'll draw that. Write a volume function in terms of x, the dimension of the square. Okay, we'll do that. Use our graphing calculator to make a sketch of the volume versus x, and determine the size of the squares that are cut away so as to maximize the volume of the box. And lastly, what is the resulting maximum volume of the box? So what is the largest box that we can make out of a 8 by 10 sheet of material? Alright, so let's get started here. It says, first thing, make a diagram of the flat sheet with the squares cut out of each corner. Okay, so let's do that. So drawing on this is not very easy, to be honest, but I'll do the best I can. So we have this rectangle, or this is supposed to be a rectangle, and we have this is our small side, so this would be a dimension of 8 inches here. This would be our large side, so we'll make that the 10-inch dimension here. Okay. All right, so that part we've started. So we need to cut out squares out of each corner. All right, so we'll label the cuts with dashes here. So there, there, and there. Those are supposed to be squares. That's not very good. I'll undo that. All right, they should be all the same size. Okay, so this is what we're trying to find. So they tell us here the dimension of the square is side x. So if that side's x and we have a square, that side must be x, that must be x, that must be x, that must be x, 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 x. Okay, now we need to finish some dimensions here so that we can get this figured out. So if we have x here, so we're talking about this 10-inch portion here. So we've got an x we're cutting out and an x we're cutting out. So the remaining part between here, between the cutouts, would be 10 minus 2x right here. All right, that'll be important. And then this way, between these two, we would have a dimension that would be 8 minus 2x right here. Okay, and that should be everything that we need for our box here. So make a diagram of the flat sheet with the squares cut out. All right, so that's taken care of. Okay, now on to the three-dimensional box. So if we look at this, we'll draw it so that this edge is the front. So this box would look something like this. Would have the front edge here. All right, and this height would have to be x, right? Because we're folding this up. So it's got to be x high. And then this dimension right here, remember, was 8 minus 2x. So that front edge like that is 8 minus 2x. And then it would go back like this. And we'll make that this dimension back here would be 10 minus 2x. Because that's this side right here. After we folded everything in, the full depth of the box there, the length of the box would be 10 minus 2x. And we'll finish drawing our picture here. All right. Okay, so that looks pretty good there. Not perfect, but that will work. All right, so that part is done. All right, so the volume, write a volume function in terms of x, the dimension of the square. Okay, so now that we have our 3D box here, it's pretty easy. Remember, the volume of this would be a rectangular solid here, basically a rectangular box. So it's the area of the base times the height. So this thing, if we write it, our volume function is going to be volume is equal to just to write it in simplest form here, I'm going to put the x first, so the height, and then that's going to be times the area of the base. So the area of the base is going to be this dimension, 8 minus 2x times 10 minus 2x. All right, so that answers that part. Write a volume function in terms of x. That's done. Use a graphing calculator to make a sketch of the volume versus x. Alright, I've gone ahead and typed that in to save some time. So we just typed this function into y equals here. And I'm going to do a zoom 6. And we know that we're going to have to fix this. Okay, so here's our polynomial. Realize we're trying to maximize the volume, and volume is our y in this case, so we need this local maximum up here. Obviously, this part right here is not going to be in play because we can't have a negative volume, and this part is actually going on to positive infinity, so we ignore that. So we are concerned about this local maximum value that's up here somewhere. So that's occurring somewhere between 0 and 1, 2, 3, 4. So let's look in our table to set our y max. So I have my table set from earlier, so let's start it at 0. And it looks like we have a max on our table of 48. So let's set it to be y max of 60 and graph it. See how that looks. Okay, so this is what we're working with right here. So instead of I'm just going to bring it over here so we can talk about it. So we're concerned about this point right there. So we need to use our max, second trace max, number 4. Left bound 0, that's fine. Right bound 1, I can type 3 here to make it quick. Guess, just hit enter. And here is our max. So I actually bring that over and replace this picture. All right, so just put that right there like that. And we've got our maximum value here. All right, so that's going to be important here in a minute. It says use a graphing calculator to make a sketch, determine the size of the squares that are cut away so as to maximize the volume of the box, and what is the resulting maximum. So we have actually figured all of that out by finding that maximum. So our sketch, which we have from our calculator, looks something like this. All right, and this would be our volume here, and this is x, the size of our cutout, and this point right here, that maximum was the key, and it is 1.47 for x and 52.5 for y. So determine the size of the squares. Well, that's just x equals this x coordinate of this maximum. So approximately 1.472, we'll call it. That's in 1,000th of an inch. That dimension is in inches, so that should be good enough. And then our volume would be cubic inches, and that is 52.514 inches cubed. All right, and that is going to be it for this problem. All right, let's look at the next example. All right, here we have example 2, a box with a lid. So we have a box with a lid is to be made from a rectangular sheet of cardboard 18 inches by 8 inches by cutting out the same small square from the two corners on one of the 8-inch sides and long rectangular cutouts from the opposite corners. All right, this will make more sense in a minute. Fold up the sides to form a three-dimensional rectangular box. So we need to make a diagram of the flat sheet with the cutouts that they are talking about here. Make a diagram of the 3D box. Write a volume function in terms of x, the common dimension of the cutouts. Use a graphing calculator to make a sketch. Determine x so as to maximize the volume of the box, and answer the question, what is the resulting max volume of the box? Okay, so first we have to make this cutout. So, or this sheet that we're using. So something like this. That's terrible. Let's try that again. It is difficult to draw on this, and that's not a lot better, but I'm going to stick with this one. All right, so we have the 8-inch side would be here, obviously. So this dimension would be 8 inches, and this would have to be our 18-inch side, like this. Okay. All right, and they're telling us to, on one side, to cut out the two small squares. So we'll do that right here. So we'll label those with dashes. So there and there, and that has to be x, 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 and x. Okay. And long rectangular cutouts from the opposite corners. Okay, so if we think about this, we've got to fold this thing up and then fold it over, because we have to have a lid for it, basically. So we're going to split it right down the middle at 9 inches. So that's a fold right there. And then I really need to hatch this because that's being cut away. And then we would have these long rectangular cutouts like this and like this. Okay, and all of this is going to be cut away. All right, so all that'll be cut. And in order to keep the sides of the box the same, we're going to have this has got to be x right here, and that would have to be x right here. And then we need, once we cut this out, we've got to have this back edge fold over. So that would be actually a fold right here, and that would have to be x. This width would have to be x right here. So it's kind of hard to see, but that would need to be x in order to fold up the back side of the box. So actually this part right here is going to end up being the lid when we're done. All right, let's see. Let's label this 9 inches here and here. We split it down the middle there. And then if this was 8 inches, this new dimension right here is going to have to be 8 minus 2x when we're done. And this dimension from here, do this in another color, from here to there is going to have to be, this whole thing is 9 inches right here from this edge to where this fold will be. So it's going to be 9 minus x right here, right up to there. All right. Okay, so make a diagram of the flat sheet with the cutouts. That's done. Now we need to make a diagram of the 3D box. All right, so the front edge of the box, front, is going to be this right here. So that dimension would be 8 minus 2x. And then on the way back, it's going to be this dimension right here. So that's 9 minus x. And let's draw the front edge of it here. Yeah. All right. Like that. And then we're going to have the lid coming up over it like this. So we'll draw the lid like it's been raised up here, kind of. All right, and then we would have this edge right here. Okay, not perfect, but this is the lid right here. It's been folded over. So this part is folded over. Okay, so this area right here, just so we're clear, is this little area right there. And then this fold right here is going to be this side right here. And the lid, we've already labeled that so that we're clear of what we've actually done here. Okay, so diagram of the 3D box, that looks good. Next, write a volume function in terms of x, the common dimension of the cutouts. Okay, well, we did this on the first example, so this won't be too bad. Its volume is equal to the, I didn't label the height here, that was x, so let's go back and do that. So it would be the height times the area of the base, so that's 8 minus 2x times 9 minus x. Okay, so that's our volume equation. And now, now we need to use a graphing calculator to make a sketch. So let's bring that up, clear out the one from the problem before. X parentheses 8 minus 2x, close parentheses, new parentheses, 9 minus x. All right, we had our previous window in there, so let's see how this one looks. Okay, that actually looks okay. We don't need to really see the bottom of this thing, but they do want us to draw a sketch, so let's make our y minimum. Let's do negative 30. That should be good enough. Let's see. If not, we can fix it. Nope. So let's use our table, which I should have done in the beginning, in order to get that negative value. So negative 100 then. Negative 100 will work for a y minimum. Graph it. Alright, so I'm going to bring this over here and so that we can see that, and actually to make this even faster, let's bring that up and let's just find our maximum, right? We're ignoring all of this because this is after it drops below the x-axis. Our volume here on our y-axis is what our volume is our y-axis, so we can't have negative volume. So we ignore everything from here to the right. So we're really looking for this maximum right here. So second trace, option 4, left bound, that's fine. 1, 2, right bound of 3 will be fine. And let's bring that picture in. That graph gives us our maximum, which is what we really want, and that will help us actually finish the problem. So let's write that. So our maximum, determine x. All right, well, that's just this x value right here. So we'll make that 1.73 will be fine. So 1.73 inches on that. And then what is the resulting max volume of the box? Well, that's 57.1 cubic inches. Remember, volume is cubic. So cubic inches there, and they did ask us to make a sketch, so we can do that pretty quickly here. And the sketch, we're only concerned about really that part right there, but we'll go ahead and graph the rest of it. and this max is our most important point, 1.73 comma 57.1 was our max right there. All right, that should answer everything. So we are done with these two problems and done with this video. I will see you in the next one.